In this video, we're going to continue our discussion of data communications. In the previous video, we talked about sine waves and carrier waves. We talked about their characteristics, including frequency, amplitude, and phase. We discussed ways in which bit values could be encoded within those carrier waves by varying frequency or amplitude or phase or some combination of the above. And we concluded that video with a discussion of multi-level coding, which discusses how we might put multiple bit values or encode multiple bit values within each wave cycle. I'm going to briefly review that and then move on to a discussion of analog and digital signals and describe their differences in terms of data carrying capacity and in terms of susceptibility to error. So we're going to stick with amplitude modulation for the moment because it's actually a fairly easy one to describe. And the example on slide 5 that we had discussed of amplitude modulation with a single bit value encoded in each wave cycle used 1 volt to represent a binary 0 and used 10 volts to represent a binary 1. That gave us a relatively large distance between the two, a 9-volt difference between those two, and as we discussed on the previous slide, it's relatively easy for your ear or for an electrical device or for an optical device to detect that large a difference and therefore to accurately on the receiving end decode the bit values that are embedded in these variations in amplitude. We then move forward to an example of multi-level coding using amplitude modulation, where we doubled the number of bit values in each wave cycle from 1 to 2. That gives us 4 different relevant amplitude values, and assuming these values represent volts in an electrical signal, we used 4 values 8, 6, 4, and 2 to represent bit value pairs 1, 1, 1, 0, and we don't have an example of that here, 0, 1, and 0, 0. The advantage of that, of course, was that it doubled the carrying capacity of the wave. At the same fixed frequency, this form of multi-level coding, at least in theory, could double data transmission rate. The disadvantage was we now only have a difference between relevant voltage values or amplitude values of 2 as opposed to the 9 we had before, and as a result there is greater difficulty at the receiving end in distinguishing between different wave cycles with those various values. Okay, in essence, our receiving device has to be much more sensitive to smaller variations and be able to accurately distinguish between them in order to accurately decode or interpret those voltage or amplitude values as these pairs of bit values. Okay, so we're going to move forward to analog signals, but before I move off of this, slide, let's just ask a question. Well, if we can take amplitude modulation and push it to carry, say, 2 bits per wave cycle, why not 3 bits per wave cycle? Well, if we did 3 bits per wave cycle, once again, we'd be adding 1 more. So basically, we would need, at that point, 8 different voltage levels. Okay, 2 to the third would be 8. And so now we would have 8 different relevant voltage values or amplitude values instead of 4. And assuming that this signal and the transmission medium that carries it could, say, only go up to 8, then we would have to slice these differences even smaller. So now instead of having 2, 4, 6, and 8 be the values, now it would be, say, 1, 2, 3, 4, 5, 6, 7, 8. That would be our 8 values. From there, let's say, well, now let's push it up to 4 bit values per wave cycle. Well, we've just doubled that, so we're going to have to cut, once again, the distance between those relevant amplitude values in half. So now we're down to half-volt differences. Okay, so as the number of bit values we encode in each wave cycle increases, we need a larger and larger number of relevant values of, in this case, amplitude. And to squeeze those in the same available space, so to speak, okay, we have to shrink the distance among them. Okay. Well, if you carry that, doubling and doubling and doubling to its logical conclusion, in other words, if you go all the way from binary on one end to, what's the opposite end of the spectrum? Well, the opposite end of the spectrum is what's called an analog signal. Okay. And the idea behind an analog signal is that whatever characteristic you're varying, and whatever the value of that characteristic. So for example, say a frequency of, 20,000, or an amplitude of, say, 98.62 volts. Okay. The idea behind an analog signal is that, let's say we're using amplitude modulation and using voltage on electricity. If I send 98.62 volts, then every digit, so to speak, of that voltage value means something. Okay. So whereas with the multi-level encoding and the AM examples, the absolute value of the amplitude really didn't matter. It was simply, was it high or low? Okay, in this case, was it 10 or 1? Okay, in an analog signal, the absolute value is, in fact, jumped one ahead. The absolute value of that parameter is, in fact, the data you want to transmit. So if I want to transmit the number, 22.673, I send through a frequency of 22.673, or I send through an amplitude of 26.723, or whatever that number was. And if I want to instead send 26.724, well, then I send 22.764 volts, or 22.764, a frequency of that value. Okay, so every tiny little variation in that parameter is a tiny little difference in the data that I'm pushing, or encoding, so to speak, in that analog signal. Okay. So if we're talking about phase, okay, well, phase, we've got basically numbers between 0 and 359.99999 go out as many digits as you want. Okay, that entire range can be used to send data. Okay, I don't send zeros and ones. I send values between 0 and 359.9999999. Okay, and as many nines as the receiver can accurately distinguish. Likewise for amplitude. I have voltage or whatever I'm varying to represent amplitude. That could be 0, or presumably the channel can carry some maximum value. The entire range between 0 and whatever the maximum value of amplitude that transmission medium or channel can carry, that can be used to represent data. 0 means something, 100 means something, 50 means something, 51 means something, 51.001205 means something, and each of those is a different value. It's not just high or low, it's all the values in between, quote unquote, have meaning. Okay? Ditto with frequency. Okay, so it really doesn't matter whether we're talking phase, amplitude, or frequency. The point here is, if we're using quote-unquote analog signaling or analog encoding, well, we're not really encoding because we're not using binary values. We're not encoding bits, okay? We're encoding, think of it as base 10 numbers to a high degree of precision in the specific value of a specific characteristic of that signal, be it phase, be it amplitude, be it frequency, okay? Now, if I realize that, as in any numbering system, okay, I've got a decimal point and I have an arbitrarily large number of digits to the right of it, in theory I should be able to have an arbitrarily large number of digits to the left of it as well, but I probably, for say amplitude values, it's kind of hard to imagine a little Ethernet cable carrying, say, 1,000,000 volts. Okay. But I can certainly imagine it carrying 5 volts, or 4 volts. I can imagine it carrying 4.9 volts. I can imagine it carrying 4.99 or 4.999, or add as many zeros as you want on the end. When you start to realize that the number of digits to the right of the decimal is basically unlimited, what you realize is that an analog signal, at least in theory, can carry an infinite number of possible values. Even if I've got a fairly small range, say like here between 0 and 359, if I'm not just dealing with integers, if I'm dealing with real numbers, there's an infinite number of real values between 0 and 359. Okay, it's simply a matter of, going an infinite number of digits to the right of the decimal point. Now, that's in theory. In practice, we're not going to get to infinity. Why? Because of the problem we've already discussed when we first described multi-level coding. Okay. The receiving device has to be able to accurately distinguish between those values and quote-unquote do something with them after it interprets them as data. Okay. It's not just a matter of the receiver, it's also a matter of the transmission channel or the transmission medium or the communication channel. So for example, if I want to, if I want to use, say, 3 digits to the right of the decimal point to represent data, and I want to send the value 4.999, okay, through as, say, 4.999 volts through this wire, well, then what comes out at the other end had better be exactly 4.999, and the receiver has to be constructed in such a way that it can tell the difference between 4.999 and between 4.999000001, for example, or 4.9989999. Okay, so this idea of accuracy applies and very high accuracy requirements in distinguishing between very tiny differences between values applies both to the receiver and to the communication channel as a whole. Okay, so the issue really is best summarized in the phrase detection precision, but it's also transmission accuracy, and we'll come back to that in a minute. All right, so analog signaling is one end of the continuum. In theory, it carries a single signal event, a single wave cycle, if you like, can carry an infinite number of different possible values, encoded as frequency variations, phase shifts, amplitude modulation, amplitude changes, or some weird and wonderful combination thereof. Okay. A digital signal, on the other hand, well, what's the definition of digital? Well, the more correct term is discrete. Discrete means countable or finite. Well, there's your comparison right now. Pretty obvious one. We use the term infinite. Okay. It was infinite when we were talking about analog. Now when we shift to digital, it's finite. Okay. And of course, a binary signal is a special case of digital in which there are only 2 possible values. Okay, so at least in theory, anything less than infinity is digital, okay, because it's finite and countable, okay. But the 2 ends of the continuum really are binary signals, which is the lowest capacity, if you like, digital signal, and analog signals all the way on the other end. Okay, so in a single signal event, a single wave cycle if you like, a binary signal can only carry one of 2 possible values, whereas an analog signal can carry, in theory, any one of an infinite set of possible values. Okay. Now, another thing with digital signaling. Thus far we've talked primarily about sine waves, okay, but if we are going to send a digital signal from one place to another, and if it's only got one of 2 possible values, well, as we've already seen, we can use a sine wave and encode that 0 or 1 as high or low amplitude or high or low frequency or a phase shift, and as long as we've got a big enough gap between the 2 values, the receiver on the other end is probably going to be able to tell the difference. When we get into pure digital signaling, however, typically we abandon the concept of pure sine waves, and we prefer instead to use something called a square wave. Okay, and a square wave, not surprisingly, looks like this diagram we have on the right. Instead of having that nice smooth rise and fall as we had in all the previous examples, note we have instantaneous shifts from between 2 values, and think of this as voltage again if you like. So here's a square wave where 0 bits are encoded as 0 volts and 1 bits are encoded as 5 volts. And I don't really have cycles now because I don't have that general rise and fall, but I still have the same concept of a time period. There is a time period time here between 0 and 1. Call that seconds, call that millionths of a second, call it whatever you want. Okay, but there is a short time period during which the voltage value is held constant, and that represents either a 1 or a 0. Okay, so the same value we've encoded in the 3 previous examples, 1101, 001, here it is encoded as a square wave. Okay, so I've got 2 high 5-volt periods followed by a no volt period, followed by a high volt period, followed by 3 0-volt periods, followed by another 5-volt period. Okay, and the concept of doing that for a fixed time interval is essentially the same, except now it's not a cycle, it's simply what is the time period. Okay, so if you were to say peer down inside the system bus of your computer, okay, what you would find, and you could watch, the bits zipping by on the electrical traces on that motherboard, what you would see is square waves moving through there. The ones would all be amplitude peaks or amplitude constant, high amplitude, and the zeros would all be low constant amplitude. Now, that works fine in a system bus. Okay, where it tends to fall down is as the length of the transmission channel gets longer. Okay, and why is that? Well, that's what we're going to talk about on this slide. Okay, so let's first just come back up to the issue of what does the receiver need to be able to do. The receiver needs to be able to quote-unquote see an abrupt shift in power levels. Okay, so the power levels have to be far enough apart that it can see that shift. It will detect that difference, and then it will interpret that difference as a bit value. So high or low, 0 or 1. It also needs to know where one bit ends and another bit begins. Okay, in other words, these time marks here, as for the sender and the receiver, pretty much have to be the same. Okay, we'll later call this clock synchronization. Okay, but the bottom line is we both have to be counting time using exactly the same starting point and ending point, and we have to be dividing that time up into the same size slices, okay, in order to accurately detect the high voltages and the low voltages. Okay, so now, why do we have a problem? Well, here's the problem we have. We discussed in the first video, we talked about the fact that although we can model things as sine waves, the world is usually full of complex signals. Okay, and a square wave is in fact a complex signal. Okay, you may not realize it, but this wave right here is actually produced by adding together a very large or up to an infinite number of sine waves of different frequencies and amplitudes. We're going to pick up on that theme a little later on when we get into bandwidth. Okay, but for now, simply realize that this is a complex signal. Okay. As that complex signal moves through a transmission medium, particularly a long transmission medium, it's going to be affected by a number of things that we're going to discuss on later slides. One of them is called attenuation. Its power level is going to drop. Okay. Another possible thing is distortion. The signal may interact with the medium in a way that changes the signal. Another one is called electromagnetic interference, assuming we're talking about an electrical signal. Radio waves, nearby transformers, 2 lines carrying different data streams running right next to each other. All of these can cause an interference that changes the signal. Okay. What happens as this signal traverses down the line is that these 3 things combine to take that nice, very square shape and turn it into something that's not quite so square, as we show here on the right. What happens is these sharp corners, these abrupt shifts in power, precisely aligned on these clock ticks, if you will, okay, they tend to get lost, okay, and as the signal travels down, it flattens out, okay, And by the time you get to the end of a fairly long chain, what went in, as shown here on the left as A, may come out as B. Okay. Now, what's the problem? Well, the problem is this signal on the right is a lot tougher to decode than the one on the left. Okay. So note that we're not holding 0 here now for the entire first clock tick. Okay. It starts at 0, but by the time we get to the end of the clock tick, it's almost up to 2. Okay. Note now that in the middle of the second clock tick, the peak is no longer at 5. It's down around 2.5, 2.6, something like that. Okay. So whereas a device that was expecting 0s or 5s held for whatever this duration of time is would work very well with the signal on the left, it's going to definitely have problems with the signal on the right. Is this first thing going to be interpreted as a 0 or a 1? Is the second one going to be interpreted as a 0 or 1? Okay. So what's going to happen is the error rate's going to go up. Okay. The error rate interpreting a signal like this one is going to be very low, approaching 0. The error rate interpreting a signal like the one on the right is going to want to be very high. Okay. The distance that we can send a square wave down a transmission medium before attenuation, distortion, and EMI, conspire to turn what's on the left into what's on the right, okay, and therefore impact accuracy in a significant way. That distance depends on the characteristics of the digital signal and of the transmission medium, okay. If, for example, we're talking about, PCI bus, okay, given the voltage levels used, given the characteristics of the traces on a typical motherboard, given the accuracy of the devices that we usually attach to a PCI bus, okay, realistically we're talking a meter max, okay, and that's probably too long. Realistically, we're probably talking a half a meter or something like that. Let's say Ethernet. Let's say we're pushing, 5-volt electrical signals through twisted pair, relatively skinny wires, okay, routed through ceilings by fluorescent light fixtures and things like that. Okay, for that, 100 meters or so, probably about the best we're going to do. If, on the other hand, say we're pushing a optical square wave through a very expensive single mode fiber optic cable, then now we're probably talking 20 miles or so, okay, maybe even a little longer. Okay, so the bottom line is you can play games with signal characteristics, high power versus low power, low frequency versus high frequency, optical versus electrical. You can play games with buying better transmission mediums that are less susceptible to attenuation, distortion, and EMI, but unless you can drive this to 0, which you can't, okay, unless you can make these problems completely go away, which you can't, over some distance, what's on the left is going to turn into what's on the right, and your ability to accurately decode that signal and extract the data that the receiver put in it is going to disappear. Okay. All right. So how does digital signaling deal with this, problem of EMI and attenuation and distortion and, the combination thereof? Well, recall that we'll go back to the simple analog or amplitude modulation example. Okay. Here's our simplest amplitude modulation example. We had a binary 1 bit per wave cycle. Binary 0 was represented by a 1-volt peak. Binary 1 was represented by a 10-volt peak. Okay. We've got that 9-volt difference. Okay, that's a big difference. Now, based on what we've just discussed, the fact that, 0 or attenuation, distortion, whatever, analog or digital, whether we're talking square waves or sine waves, if the receiver puts 10 volts in for whatever this time period is to represent a 1 bit and then sends it down the line, what are the chances that exactly 10 volts are going to come out the other end? Okay, answer, pretty low, unless that distance is very, very short. Attenuation is going to drag voltage down. Distortion, may drag voltage down somewhat. EMI may drag it down or push it up, depending on what the nature of the voltage is. So the bottom line is we wanted to send a binary 1, so we put 10 volts into this for whatever fraction of a second this cycle represented. But what came out on the receiving end was something other than 10 volts. Okay. How do we deal with that and in terms of receiver accuracy? Well, the concept here is a fairly simple one. It's the concept of a threshold. Okay. Threshold. So let's not do 1 and 10. Let's do 0 and 5, for example. So if I'm going to represent a 1 bit using 5 volts, okay, and I'm going to represent a 0 bit using 0 volts, okay, then on the receiver end, I don't look for exactly 5 or exactly 0. What I do is I simply look for something in the middle, and is it less than or greater than that? So here I've cut it exactly in half and made a threshold of 2.5 volts. So the sender puts 5 volts in to represent a 1 bit. It heads down the line. What comes out at the end is, say, 4.92. Okay. Well, I don't discard that because it's not exactly 5 or 0. What the receiver does is not look for exactly 5 or 0. What it says is it above or below 2.5? In this case, 4.92 is above 2.5, and I therefore interpret that as a 1 bit, even though it's not exactly the 5 volts that were put in by the sender. Okay. On the other hand, let's say a sender sends 0 volts, but, along the way, EMI adds a little bit of voltage, and what comes out at the other end is, say, 0.7 volts. Let's say we got a bad noise spike there because some motor started up right next to the wire as the data was moving through it. Okay. So the receiver sees 0.9 volts, says, well, that's not 0.5, but it is less than my threshold value of 2.5. Since it's in this range here on the left, that's interpreted as a 0. Okay. Why is this so? Why do we do it this way? Okay. We do it this way because we know bad things are going to happen to a signal. Okay, there's no way to control. We can minimize the occurrence of bad things. We can throw money at the problem to reduce the probability. But the fact is we can't drive the occurrence or the incidence or the probability of quote unquote bad things happening to a signal to 0. Okay. So what we do is we use this threshold-based comparison to decode the data. That way we have quote unquote room for bad things to happen. Okay, and they have to be really bad in order to have the receiver make the wrong decision as to whether the incoming signal represents a 0 bit or a 1 bit. Okay, so this idea of a threshold is basically, it's slop. This is slop factor. Okay, fudge factor. Okay, so you build in a fudge factor into the transmission scheme. Okay, and this, you give a fairly wide variation, or the widest variation you can, between what represents a 0 and a 1. Take a threshold in the middle, and basically the wider the range, the wider the range between the 0 and the 1 value you start with, okay, the bigger the range, the two halves of this range, and therefore the more room for a bad thing to drag 0 up towards the threshold or to drag 5 down towards the threshold, but without changing the interpretation once the signal is received by the receiver. Okay. So, fundamental concept in digital transmission, okay, or binary transmission. Okay. Pick two values that are as far apart as you can and interpret the bit value not as exactly one of those two values, but relative to a threshold somewhere in between them. Okay. Further apart, the bigger the ranges, the more bad stuff can happen to the signal without causing the receiver to incorrectly interpret the data. Okay. Or margin of error, if you like. It's a margin of error issue. All right, we are now in a position to talk about error and capacity with respect to analog and digital signals. Okay, so let's take analog signaling. Okay, as we've already discussed, with an analog signal, every minor variation in a parameter value, be it amplitude or voltage, phase, whatever, has meaning. Okay, there is 4.9 versus 4.90001. Those are two different values, and that difference is important to us. Okay. In binary signaling, on the other hand, it's either above the threshold or below the threshold, so we get a 0 or a 1. Okay. So there's our basic comparison between the two. Okay. Analog signaling, by its very nature, is maximizing transmission capacity. Because, once again, in theory, during each signal event, define that however you want, say 1/1,000,000th of a second, I can, in theory, put through an infinite number of different numeric values encoded as, variations in whatever parameter I'm playing with on that signal. Okay. But because each tiny little difference means something, any change in the signal whatsoever, the slightest rise or fall in voltage, the slightest shift in phase as it moves down, the slightest shift in frequency as, say, the radio wave moves through the atmosphere or moves through space, that generates an error. Okay? So, analog signaling, what I'm doing is I am maximizing transmission capacity, but opening myself up to a significant probability of error. With binary, I'm doing exactly the opposite. During any single signal event, I can only carry a 0 or 1. Okay. And if I want to carry, if I want to send a value that's much larger than 0 or 1, well, I have to take that value and I have to represent it as a binary number and send each of those bits in that binary number one at a time down the line. Okay. If it's a large number, that's a big chunk of bits. It takes me many more signal events to carry that value than it would if I could, say, take that value and just encode it in one analog signal event. Okay. So my data transmission capacity is significantly less, but my susceptibility to errors is also significantly less because I've got this concept of a threshold and I've got the slop factor, or the margin of error, built in. Okay. So, you're a computer designer or you're a data transmission designer. Which do you want? Do you want high capacity, but knowing that you're going to get a lot of errors? Okay, they may be small errors, but you're going to get them. Or do I want to trade off transmission capacity in order to minimize the chance of error? Well, which is more important to you, capacity or errors? Okay. In most cases, when we're dealing with computers, we're concerned with errors. I mean, what are the numbers that these computers are passing back and forth represent? Let's talk e-commerce. Do you care if the data transmission representing, the price that you are about, the sale amount that you're about to have charged to your credit card is accurate or inaccurate? You probably would very much like it to be accurate. Particularly, you'd like it to be accurate, past a penny. You certainly wouldn't want a situation where, some electromagnetic interference or whatever at the wrong time caused you, to have 12 zeros added to the amount that was about to be charged to your credit card or deducted from your bank because you were using a debit card, so on and so forth. Okay, so summarizing this, we could dig into more detail, and that's what this middle of the slide is, but I'm going to skip over that. Analog signals give you very high transmission capacity, but also give you very high error rate. For the vast majority of uses that have anything to do with computers and software, that trade-off is unacceptable. And that is why you don't see analog signals or analog encoding of data used in computers. Okay, at least not today. Once upon a time, back in the early days of computers, some folks played with those. But they just weren't accurate enough for the kinds of things people wanted to use computers for. I mean, think about what people used computers for, in the earliest days of computing. They used them to crack codes. Okay, they used them to fire off a shell and try and hit a ship that was, 10 miles away. Later on, they used them to, try and put a space capsule into outer space and have it accurately orbit the Earth and be able to come back in one piece. Okay, and of course IBM was busy, back in the 50s building machines that allowed you to accurately compute insurance rates and actuarial tables and, keep your debits equaling your credits and so on and so forth. Okay. The bottom line is we value accuracy more than we value transmission capacity for the vast majority of things we use computers for. Therefore, data transmission within the computer as well as data transmission between computers is based on digital signals. That concludes this video.